In Wi-Fi configurations, the 40 MHz channel width in 2.4 GHz radio and 160 MHz channel width in 5 GHz radio are very special because they are both the extreme way of bonding multiple 20 MHz channels together. In my previous video, I talked about 40 MHz channel width. In this one, let's discuss the 160 MHz channel width in 5 GHz radio. This is my lab environment. I have 5 different Unifi access points plus an UDR. I use 4 different Mac machines to test the different Wi-Fi standards from Wi-Fi 4 to Wi-Fi 6E. In some situations, I need to capture the Wi-Fi frames to better understand how things work. So I use another Mac to capture packets and to view them in Wireshark. This Linux machine has 10 gigabits Ethernet connection to the switch. It has enough bandwidth for speed testing. Of course, in this particular video, not all the devices are required, but I'm going to use the same lab environment for multiple future videos as well. 5 GHz band is much more complicated than 2.4 GHz. In the US, there are a lot of rules from FCC about 5 GHz. In this Wikipedia article, if you click US, you can find histories about different ranges in the band. In the right side Wikipedia article, you can find 8 ranges of 5 GHz and 6 GHz WLAN. You can also see the names for each range. In the Wikipedia WLAN article, you can find all the allowed channels in 5 GHz band in different countries. For example, in the US, for this particular column, from channel 32 to channel 177. They are showing green color, which means they are allowed in the US. However, if you go to Network Controller, click on the U6 Enterprise, for example, in the settings for 5G, you can see only from channel 36 to 165 are allowed. So let's look at this top left diagram. In this video, let's focus on the range from this one, which is for channel 36, and this one, which is for channel 165. These are the allowed ranges in Unifi AP for 5 GHz. You may notice already not the complete range is available for Wi-Fi. You can see 4 different blocks. If you want, you can refer to the bottom right article for UNII. You can find what are the names, what are the ranges. There are gaps in the available range, which rarely causes some problems, including the usefulness of 160 MHz channel width. You will see later. In this diagram, each shape represents one channel, which you can see in the Unifi network controller. Each bar is 20 MHz wide, and I put all the available channels from Unifi Network Controller into this 5 GHz radio band. So you can briefly have an idea about how the 4 blocks are distributed in the band. Even though each channel can be selected in the Unifi Network Controller individually, it doesn't mean they are equal. And you can also see there are different colors. For example, this reddish, yellowish colors, I use them to represent the so-called DFS channel. In the Wikipedia article I show you in the lower right, you can see what's DFS. It stands for Dynamic Frequency Selection. Basically, it's about military radar, satellite, and weather radar. Even though you can select them in the network controller for your AP, the AP needs to first make sure there's no interference from the radar, then it may use them. Now let's talk about 160 MHz. Let's play a game. On the screen, I placed 2 wide shapes. Each one of them is 160 MHz wide. Let me try to fit them to the available ranges. So I can put one here and put another one here. But can I put 2 in the middle area? No way, there will be overlapping, right? Then can I put one in the right area? no way, it's not wide enough, it doesn't fit. So it's an easy conclusion. This is the only way to put the two 160 megahertz chip into this available 4 blocks. In the lower left Wikipedia article, you can find the same information. For this column, 160 megahertz, if you scroll down, you can only find two possible 160 megahertz ranges. The same result as what we see in this simple game. Now let's talk about another thing. 80 plus 80. 160 megahertz channel width is nothing but a contiguous way of bonding 8 adjacent 20 megahertz Wi-Fi channels together. Some vendors also support a so-called 80 plus 80 mode, which is a non-contiguous way. Instead of a channel with 160 megahertz, put two separate 80 megahertz ranges. They can be combined together. The apparent benefit, of course, is flexibility. Now you can have more chances to get two working 80 channel widths. For example, for the 160 Hz situation, you won't be able to have a channel here, but now you can because you only need 80 megahertz width, right? But whether Unifi AP support it, we will find it out later. Okay. After discussing the 160 MHz 101, let's see how it works in Unifi world. In Unifi Network Controller, go to Devices. Among all the access points I have in my lab environment, only this one, U6 Lite. If you go to Settings for 5G Hz radio, you can see it doesn't support 160 megahertz width. So this is the only AP which doesn't support 160 megahertz in 5G Hz. Even the UDR, its Wi-Fi also support 160 Hz. Let me show you. See for 5 gigahertz, 160 megahertz option is here. For all other APs, they are more advanced. Of course, they support it. So in this particular video, I will only use this U6 Pro as an example. I won't use the other APs. Go to Settings, Wi-Fi, and for SSID ZU6 Pro 5G, you can see it's being broadcasted only using the one AP U6 Pro. It's only using the 5 gigahertz Wi-Fi band, so our clients won't connect to other Wi-Fi band. In Devices, click on U6 Pro, go to Settings. In the 5G section, I already chose 160 MHz channel width. And for channel, see the left side diagram for the first block. Let me choose a channel in the middle, for example, 48. Okay, apply changes. Now we are good in the Unifi Network Controller settings. Let's check the backend configurations using SSH. In the lower part of the screen, I already launched 3 terminal windows, each one for one SSH session to the same Unifi U6 Pro AP. I launched 3 of them because I want to show you 3 different results after we change the channel setting. Remember the current setting? Channel 48, right? So in the first SSH session, let me run the command IWDEV to see all the wireless devices. Let me scroll up a little bit. Yes, for this particular interface, ATH2, you can see it has the SSID ZU6 Pro 5G. That's the one we just set, right? See the channel width is 160, correct? And the channel is 48, correct? And let's see the centered frequency. It's slightly different than the 48. So hold the thoughts. Let's change the channel a little bit. This time, see the left side diagram. The very first channel is 36, right? So let me change to 36. Apply changes. Wait a little bit till the provision is done. Now in the second SSH session, let me run the exact same command. See the same interface, ATH2, yeah, 160 megahertz, channel 36, yes, that reflects our changes. But see the center channel, it's exactly the same as the previous one. You may already know why. Then let's proceed to the third session. This time let me change to the rightmost channel in the left area. Let's change it to 64, right? Find 64. Because it's DFS, the provision and waiting may be longer. Give it some time. Okay, change is effective. Run the same command in the third SSH. For the ATH2 interface, the channel 64, correct? The center, the exact same old value. No matter what's the channel you change to, as long as your channel is in the left area, center frequency is the same one. Why? Because there's only one way to put this 160 megahertz channel width, right? So no matter how you change it, it's the same 160 megahertz channel. So that's why the center frequency remain the same. When bonding narrower channels to a wider channel, the primary channel is used for signaling and for backwards compatibility, and the other narrow channels, which are combined, they are only used when sending data at full speed. This channel number you set here in network controller is for signaling and backwards compatibility, and the center frequency you see here determines the complete 160 Hz channel, and the complete 160 MHz width is only completely used when sending data at full speed. Now let's move on to the second area, which is wider, and it has channel from 100 to 144, right? Let me first try 100. Then in the first SSH, let me run IWDV, and you get the result here. Move on to a different channel, and let me change it to something in the middle, say 128. In Unifi Network Controller, change to 128. Because it's DFS channel, so I already give it enough time. Now let me run the IW command for ATH2 device. Yes, that's expected, right? Also the same center. And the reason I tried 128 is, see this diagram? If the 160 megahertz channel width is placed like this, the 128 is the last channel which will be part of this channel width. So starting from 132, it shouldn't be available to set as 160 megahertz already. But to my surprise, in Unifi Network Controller, for the 5G Hertz setting, when the channel width is 160 megahertz, the maximum channel you can select from is 132. That's what I don't understand. That's why I want to try it. But at least so far, we already tried 100 and 128. They both work, right? Now let's try 132. In Network Controller, change to 132 and give it enough time, because 132 is also DFS channel. See, even from the Insights tab of Unifi Controller, you can already guess the result. See, it's still showing 128. But let's confirm in the backend in SSH. Yeah, it's confirmed. It's still showing the change before 132, which is 128, and the same center frequency, right? You can even check this Wikipedia article. See this 132 channel, it's not part of the 160 megahertz channel width at all. This article also confirmed 132 doesn't make sense. So maybe it's a ubiquitous bug. Here it shouldn't give you the option of 132. If I'm wrong, let me know in comments. Another thing is about 80 plus 80 mode. The fact that Unifi Network Controller does not allow me to choose channels beyond 132 makes me believe Unifi AP doesn't support 80 plus 80 mode. But just to confirm that's the case, let me check the beacon frame using Wireshark. On the screen, I already opened a captured file using Wireshark, and I filtered the frames using the AP's MAC address, and I can pick any beacon frames because you can see they are all about the same SSID, so it doesn't matter which one I pick. Go to the last section, the wireless management. Go to tagged parameters, then expand the VHT capabilities. And in the second row, you can see now the current value is 01, which means it supports 160 megahertz bandwidth. So here you only see 01. And if you see 02, that means it supports both 160 and 80 plus 80. Because the value is 01, which means it doesn't support 80 plus 80. Okay, so now we are clear about from AP perspective, it only supports 160. But now let's check different Wi-Fi clients to see the interesting different results. I'm going to show you the 4 different results from 4 different Mac machines. Because they were produced in different years, they support different Wi-Fi standards. It's perfect for our testing. On the screen, you see 4 remote desktops to the 4 Mac machines. I have already connected all of them to the same SSID. Let's check them one by one to see what are the problems, what are the interesting facts we can observe. Start from the oldest Mac machine, and it only supports Wi-Fi 4. In my understanding, it shouldn't be able to even connect to 40 megahertz. Let's check it. Okay, interestingly, it shows the correct channel 128 and it's 5 gigahertz. No problem, it's DFS, correct, but it does say 40 megahertz. I can't believe it. There must be something wrong. We will validate this 40 megahertz thing. But at least now you can see, yes, it's able to connect to the SSID, even though it doesn't support 160 megahertz channel width, it can still connect. Now move on to the Intel Mac Mini. It's pretty old. It only supports Wi-Fi 5. This is also interesting. You can see the physical rate 1300 megabps. It's not slow at all. See here, NSS 3, basically it means the number of antennas. It's 3. Nowadays, for the Apple Silicon Mac machines, they only support 2 antennas. So the 3 is already a surprise, and the rate 1300 is also a surprise, especially to a machine that's so old. We will check the details later. For now, let's move on to the Mac Mini M1. It's not old at all. It supports Wi-Fi 6, but not Wi-Fi 6E. You can see it's okay. The rate is 1200. That's expected. And the NSS number is 2. That's also expected. But interestingly, you can see sometimes in the channel part, you can see it's showing 160 megahertz, and then it changed back immediately to 80 megahertz. The 160 megahertz thing is suspicious because I know this Mac doesn't support 160 megahertz. Later we will validate again, but at least we see 2 interesting things. It's even slower than the previous Mac Mini, and it seems something wrong. It's reporting 160 megahertz sometimes. Okay, the last one to check, the latest Mac Mini M2. You can see, no surprise, the physical rate is 1401. That's expected super fast physical rate. Of course, it's not super stable. Sometimes it will change back to a slower rate. And in the channel part, you can see, yes, it's 5 gigahertz and it's 160 megahertz channel width. Perfect. It's the first one. We are confident and we know it does support the 160 megahertz. So now let's spend some time to check the Wireshark package to understand their different behaviors. For the oldest Mac machine, we have a question about why it's showing 40 megahertz here. It doesn't look correct. Let's validate it using the MCS index table first. So see here, we get MCS index 15. So we get this line and we confirm the NSS, the spatial stream is 2. So then the only match is this one, 130 for the physical rate, right? See what's the channel width for this rate is 20 megahertz. So this MCS index already confirms information shown here in the Mac OS is incorrect. Okay, let's look into it furtherly by checking the captured Wireshark packets. Pick the association request frame, click on it, then go to the wireless management, expand the tagged parameters, expand the HT capabilities, and as you can see here, the second row, supported channel width, transmitter only supports 20 megahertz operation. Just by this captured wireframe, it also confirms it should be 20 megahertz instead of 40. Okay, so we are good about this Mac machine. We know even though the AP is pretty new, it's broadcasting using 160 megahertz channel width, our very old Mac machine can still connect using the 20 megahertz channel width, even though the speed is not fast, but it's better than nothing. Okay, move on to next one. To save time, I won't spend time on explaining the MCS index, and I'm going to quickly show you the captured wireframe for the Intel Mac Mini. Under VHD capabilities, it's showing supported channel width set, neither 160 MHz nor 80 plus 80 supported. It is saying for 5G Wi-Fi, it doesn't support channel width wider than 80. So that's why here you can see it's using 80 MHz channel width, even though our AP is set to use 160 MHz. Now let's talk a little bit about the NSS 3. Before Apple Silicon, Apple used the Intel Wi-Fi cards in the Macs. So 3 antennas were available instead of just 2. One benefit was in some situations, the old Intel-based Macs could get faster rates than the most recent, much more expensive Macs when working with the same access point. You are already seeing the effect, right? So this Mac has faster speed than Mac Mini M1. Okay, now move on to next machine. For this Mac Mini M1, the biggest confusion is the changing channel width here. Most of the time, it's showing 80 MHz, but sometimes it will switch to 160 shortly and then switch back. In the right side, I already expanded the captured frame. As you can see, under VHT capabilities, it's already showing 00, which means it doesn't support 160 MHz at all. So how come here in Mac OS, sometimes it's showing 160 megahertz. Then let's use the information, look up the MCS table. Because it's MCS index 11 and it's Wi-Fi 6, I assume it's this row under Wi-Fi 6. Let's see whether we can get the 1200 rate. Yeah, we have 2 possible hits. One is here, one is here. We know for sure from the captured Wireshark, it's 80 megahertz. We are confident this one is what's showing in Mac about the physical rate. As you can see, it's Wi-Fi 6 and it's 80 megahertz channel width. Now move on to the last machine, Mac Mini M2. There's no surprise from the captured packets. You can see under the VHT capability, the second row, support channel width set, 160 megahertz supported. This is the first one we see in this video, and we know for sure it supports 160 megahertz. That's why theoretically it has the 2401 megabps rate. It's super fast, right? And as the last part of the video, let's test in real world whether it can really get that high speed. In the top right corner, I launched the Linux desktop. I show you 2 terminals. Both are iPerf3 servers. They listen to different port number. And in the lower part of the screen, let me run the iPerf3 client from the different Mac machines. In the left side, I already launched the Mac Mini M1 iPerf3 testing. As you can see, the speed was pretty good. Is more than half gigabits per second. And then in the right side, let's see what's the M2 performance. Okay, it's very disappointing. it's just about 100 megabits, much slower than the M1 Mac Mini. Even though you already saw the Mac M2, the physical speed is 2 gigabits, right? So you just witnessed the biggest problem for 160 megahertz channel width. Yesterday, when I did the exact same testing using the exact same environment, the speed was way more than 1 gigabits. It was pretty good yesterday. Today, it changed dramatically. The speed is not reliable simply because the channel width is too wide. There are too many factors may cause interference, may impact your speed. Depending on your device's environment, you decide to use 160 MHz channel width in 5 GHz radio or not. At least in my environment, it's not realistic because it's not reliable. Okay, this is the end of the video. Thanks for watching.